hot, hot, hot. Let's call it okay. Okay. People are doing fine. Apologize because I'm very easy to get extension with, but it means that we are opening a gap between what I'm teaching, which is start to be homework 3 by now, and which versus homework 1 that today is really final deadline, unless there is another extension, but assume that there is no. Okay, any questions about the material, the recent material? We wouldn't like to debug homeworks right now. Some homework 1, some people are still struggling, but beside it, I think that everybody should be fine. We'll have a visitor lecture actually about nerves coming up soon, I hope. Maybe even this week. Okay, at the meantime, I just wanted to reiterate a point that I made last meeting, that let's have a chat. So I said that it's very, very easy if I have the UVW camera directions. There are UVW that we have the up and look at, from which I create the vector that points upwards. It's a W, from which I create the U and V. And I said that if you like, or if your hardware requires, and we'll have both cases, that your camera is exactly at 0, 0, 0. Don't accept cameras that is elsewhere. And that you are looking down the Z direction, the negative Z direction. There is a very easy trick to do it. You still have to compute the UVWs that we had so far. The same algorithm is still applied. But instead of putting the camera exactly where it is, we will show how we just need to apply two transformation matrix that will put the camera at 0, 0, 0. So we can use the hardware that accept it over there. Or if we'll apply the very same transformation in the opposite direction, then we can assume that every ray is teleported, every ray is teleported from 0, 0, 0 back to where the camera is, which is not the origin. And so, because I don't believe anything until I see the animation, then here is our scene. You see it here in the XYZ plane, camera direction U, V, W, that you see over here created according to the algorithm that we had so far based on the up vector and so on. You see it in 3 dimensions. Here is the XY coordinate. Here is the XZ projection, XY projection. And to start with, I just apply the translation matrix. What is a translation matrix? Move everything so the I is at 0, 0, 0. That I did not find particularly surprising. That apply the translation that moves the camera. You don't change the direction of the vector UVW, but you move the camera. So now its location is at 0, 0, 0, and the same, you are moving the point that you're looking at. So with this translation, and now the vector all stays the same, so the camera image, the image plane stays the same, and we already said before that we like the image plane to be from -1, -1, y, -1 to 1, 1. But it doesn't show exactly in this example, but UVW might be completely screwed, and that's I wanted to reiterate over the more surprising part, which was that the only rotation plane that I need to consider is take U coordinate, express it in XYZ coordinates, express V, express W, XYZ, and that's a rotation matrix that you need to. And again, there are proof for it was, let's take this matrix, multiply by the vector W, and we'll get 0, 0, 1, which is exactly the Z vector. So just I wanted for myself and for you to see how does it look. So I interpolate between rotational matrix. That is never working exactly accurately, but it was good enough. So now notice the camera is where we want it to be at 0, 0, 0. And I start to interpolate between the current direction and the rotation after the XYZ. So this part is doing, and you can access it the same. So now you can see that the W direction is point up to the Z vector, as the math guarantees. The X, what coincide with a positive X, help? But to express, the camera thinks that its right side is a positive X. So now the X coincides with the positive, the U becomes snag with a positive X, and the Y snag with a positive Y. So that's the result of this translation. You can see it in 2D. You can see it in 2D or in 3D, but this rotation makes sense only after you made the translation, so the camera is in the right place. Okay. Enjoyed seeing it moving slowly, so I can finally understand what's going on. Okay, we talked about the basic ray tracing algorithm. We talked about this part, find the T-mean, the smallest object that you're talking about. What is our plans? Next is to talk about ambient the fuse and specular shading. Specular shading is actually quite fancy when you look at the physics of it, as opposed to the diffuse that is very easy to understand. The specular requires much more physics, so we have just a model that makes something looks like the white thing. There are, I mentioned a few results, but the one that you definitely need to know is a Phong model. And next, we'll talk about refraction. Refraction. What happened to light when it goes through glass or water, vice versa. So now you can do ray tracing that hits, say, that hits a crystal ball and how its direction is changing. Okay, so for every pixel, we see what is the object that a ray through this object intersect, and we look at this code after all the parts, where we'll essentially, when we'll report for this one pixel what is the intensity of light in RGB that comes to it, we'll sum the intensity, the light, from a few types of shading and possibly a few illumination sources. So there will be a big sum per each ray. And after we are done with all these parts, just I don't believe that we'll get to it today, we will move to distributed there is lots of good reasons to assume that A, instead of shooting just one ray through the middle of a pixel, here's a pixel, that's the middle of it, instead of just shooting one ray through it, A, I will shoot a few rays through this pixel, and B, that to handle aliasing or to suggest anti-aliasing method, that I'll have to tell you what it is and why it is appearing in ray tracing if we are not doing the distributed, fuzzy, randomized things, anti-aliasing might easily pop up. And how do we handle between it? And sometimes, so we see that sometimes it's better idea to shoot a few rays through every pixel. The exact location of the ray might be randomized. That will have some advantage. And even the location of the objects themselves that we want to do, they might be randomized or translated a bit if we want to simulate effect like blurriness in the image, because the image has focal lengths and objects that are not in the focal length should look fuzzy. Or that there is motion that creates a blurriness, and we'll see how to generate this blurriness artificially. At the meantime, we went through these slides. Here are the two spheres with no shadings at all. Here is this classical object that we see with all types of shading, including diffuse, that doesn't introduce the white spots, including the specular spots that adds this brightness to the whole object, plus the white spots that are very specific parts. And each one has a different model. So the input when we are computing the shading, and mentioned shading and shadow are different things, don't get confused. Shading, we want as an input the I direction, the light direction, L, light direction to the point, V, the direction to the viewer from this particular patch of surface, and the normal to the surface at this point. They're all playing a role, all the three vectors playing a role when we are computing the surface. And sometimes there is more parameters about the surface itself. Okay, light source. At the moment, we think about point light source and what happened to an amount of photons sent from this point light source. What happened to a photon, amount of photon sent from this light source? Let's assume that it omnidirectional, all sent all over the place equally, and they are increasing the amount of light, the amount of photons per inch, now just inch itself because they're living in 2D. Of course, the same amount of photons now reach a larger and larger circle, which implies that in 2D, the intensity decreases with the radius. How? On the plane, cubically, linear.
Just like inverse square law?
I'm still on the plane, so all I'm doing is that 100 guy and 100 photons sent out. Now they're dividing it among a circle, still in 2D, whose radius is 2 pi r. R increases, so it is just the inverse. I'm lying, it's all in 2D, all non-realistic. So on the plane, had it be interesting for any reasons, in the plane it just decreases linearly, but it's not really. People on Zoom, how is the sound? You can type on chat. Okay. Now.
Sure. Thank you so much.
6. 3D. What happens? This is a sphere. What's the relationship? You might not remember the exact relationship between the volume of a sphere and the surface area of a sphere, but to get but up to different constants, it behaves just as we think about a cube. We have n r by r cube, as complicated as I can draw in 3D, r by r by r, right? So the volume will behave as r cube, is r cube. What about the surface area? There are here 6 faces, and each one has area of r squared. So the total surface area is 6r squared, so it changes quadratically. So the same amount of photons now need to divide between something that grows quadratically as a function of r squared. So that's great, except that if we'll follow it, then everything that is not near the light source will be very dim. So we don't, and if we want to show light effect at all, if we want to show the distance from the light at all, usually we'll declare that it's decrease linearly, nevertheless. And we are like, just because, remind you, we have monitors, that most monitors have color density. The values that you can assign for every pixel is between 0 and 255 when you eventually get to display it. So intensity, just to see the slides till the end, is the same intensity. I for intensity will use it divided by r squared. Shading is not shadow, we already said it. Shading is how we change the intensity when it reflects from the light. And diffuse shading and specular shading will be where it is, the math will start to kick in. Okay, now, yeah.
Can you move back 2 slides? So this is the intensity is divided by r squared. I think you said that we wanted the intensity of light to fall off just divided by the radius linearly instead of divided by
or even less. Radius by some power lesson, or not at all, depending which effect you want to do what the thing.
Okay.
And I'm proud of myself of not being ashamed to say that I don't know, and I don't know. So I don't have more rules. I'm citing what I was told. Yeah. But yeah, we'll talk about it much more when we'll talk about image, about HDR, high dynamic range, but our eye is way, way more sensitive than what a monitor can say as far as its ability to handle at the same time very dim light and very bright light at the same time. So, okay. So just to mention that coefficient, that there is an albedo coefficient, just not to be confused with the ambient coefficient. Just like in general, every material observes some light independent of its color, where we consider that among the natural part, coal is as low as it can get, returns as little light. I'm not talking about the type of the colors that is returned. I'm talking about energy-wise, how much is returned versus how much is observed. Then you'll get very little in the coal, and snow will be pretty much as high as you can get among the natural material in terms of energy return. Why don't I have coal over here? I don't have coal. Okay. What is the ambient coefficient? In all your graphical in programs, OpenGL, Blender, you'll be asked to give at least one set of parameters RGB for each object. If you want, you can give more. But the first is just what is the ambient coefficient, which is a coefficient for the red, a coefficient for the D, and a coefficient for the B, and this is all for a ambient part. So an object is blue if out of the RGB color that hits it, it returns mostly blue light and much less of the other three channels. Makes sense. So three coefficients, each one is between 0 and 1. And it assumes, if you want, that if you're talking about one of the graphical graphics interfaces, Blender, for example, OpenGL, for example, put a blue light and illuminate by it a red object, supposedly it should be dark. And that's exactly what would be the effect. Or we can assume that there is ambient atmosphere, and that's just how you show the color. In homework 2, you ignore source of light unless you want to already program color, but you will have it in homework 3, so maybe you want to already to implement it. Yeah.
So this is obviously geared towards visible light modeling. Is there a way to say model like infrared light via graphics? Like, is there like the fog model? I imagine is mostly for the visible spectrum. Is there anything that does like infrared, for instance?
You think about the connection as a color to see, or as a returning, if you illuminate by infrared, well, had I been physically loyal, I should not concentrate only on RGB. I should concentrate about every frequency, exactly. Every frequency that there is, and it's just because these strange artifacts that our eye is so much limited and had that RGB are just enough, and we should have had monitors with many more channels had we want to derive them from lobsters. I think that lobsters are usually the example of that they have these 13 or so types of cones and see. So I don't know if it's a good answer, but that we could have continued to give some coefficient for each type of color. It's just because our eyes are so limited that we can cheat enough with just three colors. So the very quick answer is that I think that you can do it for every for different frequency. I don't know that it will be different in any way. And it's cooler if you want to now express fluorescent objects like scorpions in dark light. That's interesting exercise. Okay. So far for ambient, just don't care about direction, don't care about creating a shadow, don't care about the source of light. Ambient light is coming from everywhere to everywhere. It doesn't affect, and unless otherwise stated, it has the same amount of RGB, no intensity. So what you see is just the RGB coefficient of each object. Okay, things are a bit more interesting when we start to talk about the diffuse. Here the physics starts to be in the game. Taking the surface, how is this illuminated to you? Look at this part. Now it's more bright. Now for the one of you that still see it, supposedly it's becoming darker and darker as far as illumination from the projector angle is considered. There is illumination from other sources, but had it been the only sources of light, the projector over there, it will become darker and darker. The more it is looking away to the light. And the explanation is very simple. But we want to say, here are my 3 photons coming from the flashlight and hits this door. So there is some intensity on this door, and right now the normal of this door is pointing directly to the flashlight. So I get, if the area of the door is 1, I get 3 photons per area of 1. Opening the door, hopefully, opening the door, now its normal is different. meaning that I still have the same 3 photons, but now they need to split over a somehow larger area. By how much is this large? So what is the ratio of the area of the door closed, where its normal was pointing directly to the light, versus the door semi-open, creating an angle of alpha? Well, do the math. The side there, this area is enlarged by 1 divided by cosine alpha. This is this cosine alpha, or this length equals this length divided by cosine alpha. So we have 1 over cosine alpha, but now we have the same amount of photons are now hitting not the normal direction, but a different direction. So the same amount of photons are divided by 1 over cosine alpha. So multiplied by 1 over cosine alpha, making it what happened to 1 over cosine alpha just give us cosine alpha. So that's how much the intensity change as the effect of the diffuse. Make sense? The intensity divided by the length of f, which is the intensity divided by 1 over cosine alpha. Whatever was the length here will be the same length divided by cosine alpha, which is just the intensity times cosine alpha. And luckily for us, we usually don't care about the angle specifically, we just care about the normals as vectors, because when we multiply 2 unit vectors, the result is a cosine. So you don't need to ever call cosine directly. You just say, oh, I have the intensity and I want to create a diffuse effect. Then, for example, I am doing the ray tracing, and my ray, here is a viewer, and the viewer shoots a ray, and once this ray hits the door, and I want to create a diffuse effect by controlling the intensity of the door. What will I do? I'll just take the RGB value, all 3 of them, the ambient coefficient, and multiply the 3 of them by cosine alpha. What is cosine alpha? It's nothing but the direction to the light, L, the direction to the light, and the normal to the door. That will tell you a number between 0 and 1 that tells you by how much should I make the door darker as it opens. Once again, source of light, normal, normal, putting in this direction, as the normal turns around from the direction for me to the light, the surface needs to be more and more dimmed. Okay, so far the diffuse shading would just say, take the light under the diffuse is the light of the ambient part, the intensity of the light that arrives, times if you want to give another 3 sets of coefficients. You don't have to, but you could give in addition to the ambient to show how much it looks by the diffuse, otherwise just use the ambient of the coefficient. And there are actually 3 equations here, one for R, one for G, one for B. For all 3 of them, you multiply it by cosine n times L. And this number, if the direction to the light, in particular, if you have a few sources of light, then it could be that this light doesn't contribute anything, but other directions do contribute. So if the normal points to me, this is the door of the surface that I'm talking about. This is the other side of the face that you don't show. Right. But had I multiply n times L, this expression should be negative, which can take away from other sources of light which you don't want. So it's a maximum between 0, you never have a negative value over here, or this cosine. Okay, and so far the way that you'll show each object, say in homework 4, would be you will have the ambient part, which means that every object is never completely in the dark. You have some ambient light, where every object has some basic intensity plus a sun that illuminates everything that it shows. There is shading, there is shadow involved, it's exposed to the sun or not, so you'll call the ray tracing recursively, but if it does see the sun, then you look at the normal to the surface. We'll talk more about how you compute the normal and multiply by the direction to the light. So these two spheres, here we don't have much ambient light, very little, very bright in the direction to the sun is somewhere here, and it's going more and more darker, the way you're getting closer to the equator with respect to the sun. Make sense? And the addition, so this equation, the intensity that you show would have some parameter, which is the ambient light, and now, of course, different depending on the color of the object. Blue would mean the blue coefficient of the ambient is high and the other two are low. And in addition, this term by itself. And if you have more sources of light, each comes from different direction, then you just add more terms to this summation. And you're just careful not to overpass the maximum values that you can give to this point. So you don't want to give it more than maximum than 255, if that's the maximum. Okay, so that is returning with respect to the diffuse. You can have it more related to the diffuse or less related to the diffuse, more ambient or less ambient. Bring us to the next slide. If you believe the literal math that I just showed you, then when I look at the moon, there is area exposed to the sun, most illuminated, and as I'm going down to the surface of the moon, the intensity you change according to cosine alpha. Cosine the angle to the sun, and the angle to the normal. The normal change its direction, so the cosine should decrease, so I should, moving towards the equator, it should be more dim, more dark. Look at the moon, sure, whatever is after the equator, not seen to the camera, is completely dark, not seen by the sun is completely dark, but moving along the surface, I don't see any decrease between this point and this point, and that's why.
Because light far away is parallel?
That just make it more accurate.
Oh,
That highlight this part more than that. I mean, you see some decrease, but very rarely.
Is it because the sun is very big?
No, that's not the explanation that the textbook suggests, so it cannot be right. Yeah, it does, part of, but it's also far away, so it can cancel out. The explanation is much simpler, and you all understand it, except that I succeed to confuse you just a bit. But
Well, are we seeing the front side of it? So really the back side is just the darker, since we're both, like the sun direction and our viewpoint is the same direction, effectively. So like we are seeing it correctly, it's just the part where it
I
stops
don't
letting
see
it
any
behind.
decrease of the intensity. That I
It's not
agree with the
intense.
slide. I don't see any decrease in the intensity until I actually hit the equator. After the equator, it's not exposed to the sun, so it's dark. No problem. But the area around the equator, there is not one particularly bright point.
Is it because the moon isn't perfectly smooth?
Getting warmer. So why is this relevant?
No, because there's a lot of details on the moon that interact with the light.
there are a lot of pieces of surfaces, craters and so on. And with all these craters, what happened to the normal inside the crater? Some points to the sun, some points away, and very not clear, then clear decrease in the average intensity as you go out, because it's so far from being smooth. There is enough many triangles, if you wish, enough many polygons in the place of the moon that has their normal points to the sun here or here or here. Make sense? Had the moon be perfectly smooth, that's how it should have looked, despite the sun being large and so on. Okay, so far with ambient shading, we had this slide before. Am I going down? Yeah. Okay. And I'm done with diffuse shading into specular shading. Play pool. Here is a black ball, and here is your ball that you want to sink into this hole or into any of the holes at the corners, but you have an opponent ball right here that blocks you from shooting directly to the ball, which implies that your way to hit B1 is by having a reflection of your ball. But so you want to hit your own ball, B, so it will bounce from the boundary and then hit B1. How should you do it? With a cute algorithm that will tell you how to calculate exactly the point that you want to aim for.
So you take the reflection of B1 over the edge, and then you draw the line and it'll cross the edge at that point. That's going to be the point of contact.
You're taking B1 and you're asking what, you're taking B, and so you're asking what is the distance D of B from the edge. And now from the edge, you're taking another direction D and shooting the ball, sorry, it was on the wrong point. You're taking B1, reflecting it distance D to the other side, creating B prime, an imaginary ball over here. You are shooting a ray from B into, this is B1 prime, this imaginary ball. How do you create this imaginary ball? By reflecting, by going in the opposite direction to the distance, and that's the direction you're aiming for. And if the physics works, then when you're projecting, when you're shooting the ball, then this angle and this angle, the perfect fable, are the same which means that a reflection of the ball from this part will hit you right here. I don't think that it was a good explanation. I should have prepared it earlier, but that's how you're computing the reflection. When you're playing pool, and that's how you'll compute reflection right here. You'll sometimes have, I'll give you later on when we'll play with shaders and RGB, questions like create a scene. I'll ask you, use a Z-buffer, the Z-buffer algorithm shaders programming, and the shader programming algorithm wants ask you to send to it sand of triangles, objects in the room, and you will create for it, and it will create for you the image that you'll see. You also have to tell you where the camera and the other camera parameters, but once you'll tell it what are the obstacles and lightning, it will create the image for you. And then in the homework, you'll have questions like create the object of the room. In this room, there are people and furniture and stuff. Here is a camera. And here in the room is a mirror. And I ask you to take a picture. So this nice person that is seen over here, or maybe another, the blue person that you see over here, you need to show in the mirror both the front face of this person as well as, if your direction is right, the back side of this person. And now it becomes a cute algorithmic question. How do you do it? Z-buffer is very efficient, but it's not well done to handle mirrors. Okay? Algorithmically, how do you handle it? And I'll let you more meditate on it slightly more. Maybe I'll ask you how do you do it, and I'll give you a hint. Z-buffer is very happy to take the obstacle and render them for you, but it also allows you to place images like billboards on obstacles, call them texture, and it will do all the calculation. So if you have on a polygon in the scene pictures, Z-buffer is happy to do everything for you, including place a picture on it. You don't need to worry about each and every pixel of any texture that you assign to a surface. And now why don't you speak about cluster into groups and try to think what's the fastest algorithm under this very, very basic model.
How do you
Just like
properly do the reflection in an efficient approach?
Oh.
You put the couple of mirrors in the truck and the reflections and see what you get. So these are the mirrors, the camera.
So you put something like that work so far.
Yeah.
What do you use for that?
So what you have to do is
Yeah.
At that point, I would just make
Probably need a series of them.
like point. There's no arrays are generated. I think it's something that you
Yeah, you need the same one, I would imagine. I think. I don't know. That's actually a good idea. Should put another camera behind it.
This is just for like a stationary rendering, right?
Stationary rendering. You know, I'll tell you about all the furniture in the room, not too many. Z-buffer does all the things that you're doing now with ray tracing. very efficient, but it doesn't handle mirror. I need to be more assertive in getting people to participate in these discussions, but next time, maybe I shouldn't give deadlines of homework at the same days that we have meetings. Yeah, you can have more time and participate, but it's too late for today. But I told you many times, I'm not very keen even about what day exactly you are submitting. Very keen that once you submit, please do your best. Talking about it, if you know that you have bugs in the homework that you submit, please tell me in the README, this part doesn't work. If you say everything is working and I'm discovering the bug, it will be, yeah.
If you wanted to simulate a mirror, couldn't you take where the camera is, move it that distance behind the scene, and then take that image and place it onto a billboard? Then when you return the original
Yeah, it's slightly more technical depending on where is the camera exactly, but what do you see in the mirror right here? Think about rays of light that are following the camera, hitting the mirror and bouncing back with a right angle. Remember, this equals this. This ray will just be what happens at the camera be somewhere on the other side, and this would be actually not a mirror but a window. So what is the algorithm that I'll ask you to implement, if it will be the same homework, would be calculate the location and parameters of the camera right here in this imaginary world. Take an image of the room, which means report to the Z buffer all the objects that are in the room just when the camera is over here. You might, and then look at the image that is created in what we call the color buffer. Look from the color buffer at the part that hits this mirror, that fits the window, place it as texture, and now do another pass from the real part of the camera. And that's how the real world is doing. Mirrors as well as shadows in many cases, because then you will ask what is the buffer when you see it from the sun, as well as total radiosity when you ask which point in the room sits which other point in the room. The buffer will help you calculate this part as well. Many algorithms start by multiple passes of the Z-buffer algorithm because the Z-buffer is quick. We actually saw it in one of our first meetings when we said, I have a very complicated scene, so to start with, I'll take one of the houses that are very detailed, place a big box on it and ask, is the whole box seen at all? Which I can do by just assign a unique color to this box, had I have a few such boxes, and ask, in this image that I finally generated, are there any any pixels of box I, any pixels of box J, any pixels of box K, and only if there are any, then I'll bother removing the box and actually show the buildings that is underneath it with all its glory. Okay, so once again, perfect mirror means P has a perfect mirror reflection of the light that the mirror. P is fully illuminated if you see the light at the mirror at this particular point, which will happen if and only if this angle equals this angle, or if I look at the normal, this angle equals this angle. Okay, so keep it in mind when we'll talk about specular reflection. So notice that even here that in this perfect mirror, think about a very dark room where this is the only source of light, and what do you see in the mirror? Every point in the mirror is completely dark, except the one single point where there is a perfect reflection of the light. The whole room is completely dark, the whole surface is completely dark, excluding this one particular point. Because that's already is an example of a specular reflection. Okay, and as we said, we can do it by computing ask what is the point of the exact reflection, look at this source light, take distance check what is its distance to the surface, walk the same distance to the other side, in other words, reflect the light source to the other direction. Now generate a straight line that connects the viewer to this imaginary source light that tells you what is a point that is illuminated. Give us a nice little puzzle. You have a bug, but which bug should it be? Probably a beetle. A beetle is here that wants to go to this point over there, and what should be the shortest path of the beetle? Cute little puzzle. How do you calculate the path of the beetle that is the shortest that gets from this point to this point? Sorry?
Straight line.
Beetle, they can't.
Oh, they fly.
That's why. I think. Do beetles fly? Some do. Yeah, this particular one don't. Caterpillar. Caterpillar, I'm sure. So, do you know? How do I compute the path of the beetle from this point to this point? Famous Google question.
The traveling salesman problem?
Sorry?
Like the traveling salesman problem?
No, it's straight line. There is nothing like it. Just there is one point here, one point here. I want to find the shortest path.
Which point?
I didn't do it. From here to here, how do I draw the shortest path? So, answer is now you planet it, draw a straight line, and now we get it. Now the planarizing the surface is not necessarily unique in the room because you have different ways to planarize, so you'll find in each one. But once you decide which edges to open, your path is well defined, just a straight line once you planarize it. Okay, given everything that we've seen about mirrors, let's ask how do I create the specular reflection. So the specular reflection, this point, should have appeared more or less, the spot should have appeared more or less where the point of the light would have appeared had the sphere be a perfect mirror. That was a convoluted sentence. When I'll generate the specular effect, I'll imagine from time to time that I replace the surface with a perfect mirror surface because they are very much related. And what's special about the special surface, the angle to the normal and the angle away from the normal are the same angle. Okay, so what do I want to detect? I want to detect the reflection director R, and had this been perfect, I want to know from this point P what is the direction where the point is reflected. You'll have homeworks where you'll have mirrors also, and then you'll do ray tracing. Here is the viewer shoot a ray from the image plane that hits this point. What is the color that I assign to the eye? I don't know yet. I need to shoot another ray in the direction reflected from the mirror. How do I compute this reflection? Here is this math. Take the R equals, take D, the direction of the ray where it hits a mirror, and minus 2 times the normal direction times n times n, because then that's a scalar, that's a vector. If you do it just once, then what happens is that you'll get a new vector that is just in the direction of the surface itself. Basically, if this vector if the normal is a y direction, then if the normal is a y direction, then this terms d times n is a y component of r. If we do it only once, you're just deleting the y component, so you're getting a vector that has only x component. You're doing it twice, then instead of here, do it once. It points to here, doing it twice, points to here. That is, you reverse the y direction, and the y component, reverse the y component, and leave the x component the same. Okay, let's assume without proof of the generality that n is 0, 1. D has two components, dx, dy. R has two components, rx, ry. And R and D have the same y value, right? A fly that moves from hits this point and reflected, its x direction, x velocity did not change. Its y velocity has completely reversed from minus to plus, and rx equal dx and ry equal minus dy. And follow the math, it just happens. Okay. So if you have array R, we talked in the last two meetings, how do I compute the meeting point of the array with the sphere? I'll go back to specular reflection in a moment. In the meantime, it's both about specular reflection, because we need it for specular reflection, but also need it for mirror spheres. You have this direction. You find the location P. How do I know what's a normal at P? The normal to the surface at P. I found P, yeah.
It's the subtracting the vector where you hit the point minus the center.
Exactly.
That's the normal.
Yeah. Everybody agrees? The normal is just in the same direction that if I go from the center of the sphere to P and I would continue, I'm on the direction of the normal. This is usually not of unit length, so you want to normalize it, but essentially P minus C gives you the normal. That's P minus C. And now you take the normal and normalize it, and then you're done. And now if you have array R that D, you have an array whose direction is D, then you take D minus 2 times normal times normal dot product D itself. This will give you the vector that is going away. And when you're doing recursive ray tracing, then from this point, you will now shoot a new ray asking what does the viewer that sits right here at P sees at this particular direction. Now, blink phone specular shading, which is again the full sentence is an approximation to this point, will say you need to see if this is the sun and here is a viewer, then at the point where the sphere has a perfect mirror, that's where I see the maximum intensity. However, the specular spots are not just a single point, they have a little area around it. And this area might be smaller or larger depending on the property of this surface. Plastic will have more larger areas than just metals that tends to be closer to perfect mirror. So what should I do? How do I know that it is a perfect reflection angle? The incoming angle equals to the outcoming angle exactly, which would mean that this angle alpha that I compute between the direction of perfect reflection and directed to the viewer, alpha over here will be very small, will be 0, where I'm exactly at a perfect reflection. What does Fong suggest? Fong suggests take this number alpha, compute its cosine of alpha, and it's a hack. We are teaching it because it works, but it's a hack. Don't ask for much rationale behind it. Takes this dot product, which is roughly the cosine. What's good about cosine? What the graph of cosine tells us? Cosine at 0 is at 1, and then at 90 it goes down slowly. And it has a nice decay. And what's the beauty about cosine? That we don't need to compute it, it's just a dot product. So every time that I wrote a cosine, it's just dot product of these two vectors. And look at this graph, it still decays very slowly. But it means that as I'm moving along this field, alpha increases. Alpha, again, direction of perfect reflection versus direction to the viewer. So that might decrease too slowly. So what does Fong suggest? Take this number, which is between 0 and 1, and multiply it by another number which is smaller than 1, namely itself. And do it 3, 4, 5 times this production, that is, compute the cosine to the power of m. M is some constant that you decide about ahead of time that is relevant to this surface. And this will tell you what is the intensity at this point. But here is an interesting point. This is not a factor of the RGB values that comes. It is the total intensity of this point, just using the intensity in all channels, right? In all RGB. Because of specular reflection physics, it will usually be at green. If your light has all three components, then I'll say it again. You're looking at this number, and you multiply the parameters of the incoming light, but what is not in the game at this part? The color of the object itself. But in the specular, in the diffuse part, it was just cosine times what is reflected from blue object, it will be mostly blue. In the specular one, no. It is just a property of the light, so if the light is white, then the specular reflection, the specular spot will be light as well, will be white as well. Okay, and that's how you're creating this specular spot over here. The center of the spot is where you have perfect incoming angle from the viewer and from the light. And as I'm moving on the sphere, of course, the normal changes, and that's why this alpha that we had earlier changes, and we are getting into lower and lower points on the graph. So if that's my attempt to create cosine, then here is cosine square of alpha, just decrease much faster. I'm doing cosine cube, cosine to the fourth, just decreasing faster and faster, meaning that the specular spot is becoming smaller and smaller. Right? So just to remind everybody, original surface, no 3D at all. No 3D feeling at all. Adding to it just the diffuse, you already see the some 3D parameters, and there are algorithms that will actually can do 3D reconstruction from such surfaces with some amount of reliability in some assumptions. You can actually create the 3D structure just from the diffuse effect. The specular spots, remember, in the diffuse, the viewer is not in the game. You don't care where is the viewer, for the specular plus a Fong effect. You ask where is the viewer. In both of them, of course, you do care about the light, about the direction to the light because of the cosine, etc. And just to see how this m is in the game, this Fong exponent is in the game. Here you see, here we called it, I called it P, so it's cosine to the power of p, sometimes called Phong exponent cosine alpha to the power of p. P is universe to this particular surface. And what happens when I increase p? It means that I am, at the point of the perfect mirror, I still see the specular spot. What happens if I'm walking just slightly away from the point of the perfect mirror? Then alpha that we had over there, moves from being 0 to be just slightly away from 0, and then cosine of p of alpha, the larger p is, then the more dramatic is a decay from 1 to 0, implying that if for a very small p you still see the whole specular spot over there, even for alpha different than 1 degree, as p increases, it's becoming more and more concentrated at just this very specific point. Yeah.
I'm sorry, is that exponent as part of the material?
Yeah, OpenGL will ask you, what do you want this exponent to be? And in homework 4, I'll ask you either assume something or or find the one that makes it looks nicer.
Does that exponent relate to the material, or is it
Absolutely. And once again, it's a hack that makes it look like it's shiny and plastic. And yes, I will argue that plastic will tend to be more smear, and metal sphere tends to be more precise. Now, there are fancier models that will try to actually take texture of the shape itself, even if it's metal and it's well done, then the polarity of the light makes a difference. And I'll give reference to more fancier models that tries to be more realistic. But Phong is a quick hack that is acceptable as doing well and very easy to compute. And so putting it together, the formula that you're putting, the intensity, luminance at this particular point is the sum of what you are showing through the ambience plus what you're showing onto the diffuse plus what you're showing for the specular, where the ambient is just the color, the intensity is the ambient. You assign it as parameters. You want mainly white light all over the place, times the coefficient. There are 3 coefficients here, RGB in every coefficient that I show. It's actually 3 depending on the color, plus, once again, you're giving it, if you want different coefficient for the diffuse, it can be the same, homework 3, 4, it can be the same, times the intensity at this color, times, again, the direction to the light, times direction to the normal. Viewer is not in the game yet. And again, make sure that it's positive, otherwise it just says nothing, it's 0. Plus the coefficient for the specular times the intensity times, once again, you want it to be positive, and now it's n times h, we mentioned before, direction of the perfect direction to the light to the power of p. I'll show you what it is. H in a second. There is a hex that makes this calculation a bit faster. Okay, and it doesn't have to be the exact angle that you are using. It could be enough. Make sure that you are not oversaturating, of course. Now, if you have various sources of light, just sum them up. Sum up the intensity from each one of them. Notice that we don't here scale by the distance to the source of the light. It's okay. It's just don't. You could, you don't have to. Okay. And once again, just the code, just summarizing it for each one of the components. You have it on the slide. We will not spend part about it. I thought that I had a slide about it and remove it. There is a little hex that prevents the need to compute what is exactly this angle. What you saw so far was computing the angle. I'll show you a little hack that does good results, and for which you don't need to know what is the angle. Remember, there was for a point P, if that's a light and that's an eye, here I have perfect reflection, but at a point where I did not have a perfect reflection to the eye at P prime, I asked, here is the direction of the ray from the light, the R prime from P prime. If I have a perfect reflection, here is the direction from the light, and here is alpha, the angle between them. And as long as alpha is small, then cosine of alpha is close to 1, and cosine to, and even if you put it to the power of P. But here you do need to compute alpha. And I'll show you next time a little hack that just do sum up two vectors, subtract from another vector, multiply dot product by another vector, and voila, takes this parameter. And you don't need to know what is alpha exactly. So no need to do cosine directly. Our next topic, light that hits glass, change its direction, and direction again when you're moving from the glass outside. We'll talk about Snell law. Show me fingers how many talked about Snell laws before. Home, everybody, half the class, something. Snell law, high school. So we'll remind you how to do it and and how to compute this direction effectively, which will help us say handle processes like how crystal ball or diffused or glasses, how do you see the world from glasses. Thank you.